right, so today I believe we're going over common collections. And I already have an editor out, but I'll open that a little bit later. Let's read through this first. Here we go. This is chapter 8, by the way. Common collections. Rust's standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values. Unlike the built-in array and tuple types, the data these collections point to is stored on the heap, which means the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and costs, and choosing an appropriate one for your current situation is a skill you'll develop over time. In this chapter, we'll discuss 3 collections that are used very often in Rust programs. A vector allows you to store a variable number of values next to each other. A string is a collection of characters. We've mentioned the string type previously, but in this chapter we'll talk about it in depth. A hash map allows you to associate a value with a particular key. It's a particular implementation of the more general data structure called a map. To learn about the other kinds of collections provided by the standard library, see, and they have a link to the documentation. What they say down here in this last line is, we'll discuss how to create and update vectors, strings, and hash maps, as well as what makes each special. And real quick, let's just see what they have in terms of documentation. Other kind of collections. Let's see. All right. Sequences, vector, vec_deque, linked list, hash maps, B-tree maps, hash set, B-tree set, binary heap. Okay, and then they have a little description of when you want to use them. And it looks like they go over a little bit over performance of each. Correct and efficient usage of collections. They have a good amount of information here and some examples. What is this at the bottom? Modules, binary heap, binary B-tree map, B-tree set, hash map, hash set, linked list, vec_deque. Little description, and then the structs associated with them. And enums, but this isn't experimental. I think in order to use experimental, we have to pass a flag to the compiler. Okay, understood. Moving on. And we're gonna need our editor. Storing list of values with vectors. The first collection type we'll look at is vect, or vectors, also known as vector. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. They are useful when you have a list of items, such as the lines of text in a file or the prices of items in a shopping cart. Creating a new vector. To create a new empty vector, we can call vect ::new function as shown below. Let's do that. Let v, and we're declaring the type vect I32. That should be the items that are allowed to be stored inside of it, and that is already imported, so we can just call new on it. Cool. That seems like it works. Note that we added a type annotation here because we aren't inserting any values into this vector. Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We'll cover how to use generics with your own types in chapter 10. For now, know that vector, the T, I think that stands for the generic, type provided by the standard library can hold any type, and when a specific vector holds a specific type, the type is specified within angled brackets. In listing 8-1, we've told Rust that the vector T in V will hold elements of type I32 type, which is noted right here. So this is the type that it's going to be storing. In more realistic code, Rust can often infer the type of value you want to store once you inserted values. So you rarely need to do this type annotation. It is more common to create vector that has initial values, and Rust provides the vector macro for convenience. The macro will create a new vector that holds the values you give it. And 8-2 is going to show us an example of this. Alright, so what they're saying here is there's two ways to sort of go about creating a vector. You can do new, but if you use new, this implies that you're not passing any values into it. As such, Rust does not know what type that you're trying to store. Thus, we have the type annotation, which explicitly tells Rust that we want to put I32 in there. However, if we knew what we were putting in or wanted to put something in there, we can say, I'll call this x. Let x equal vect, and we can use this macro as a sort of shorthand. And then we can put 1, 2, 3, and as you can see, the compiler is able to infer the type, and I32 is right there. Because we've given initial I32 values, Rust can infer that the type of V is I32, and the type annotation isn't necessary. Next, we'll look at how to modify a vector. Alright. Updating a vector. To create a vector and then add elements to it, we can use the push method as shown below. We have two different vectors. Let me just get rid of that one and stick with V. So they're saying we can do things like push to it. However, we can only push to it if we let Rust know that V is mutable. So we can do v.push, and that's right here. And 5 v.push 6 v.push. I wonder if I can print out V. I'm gonna try that next. 7 v.push 8. So we have these, but I wonder if we can print it out. Will they do sort of like a debug for us? V. Just curious. Cargo run. Ooh. Cargo. Could not compile. Does not have the pretty print. Okay, so it doesn't look like we can print it out directly. I wonder if it has the debug. Oh, here's the debug. Hey. They put it there in the error message. Get rid of this. And it looks like if we print using the debug syntax, then yes, we can print it out to screen. That's good to know. And as you can see, we push 5, 6, 7, 8, and they are right here. All right, let's continue. Dropping a vector drops its elements. Like any other struct, a vector is freed when it goes out of scope, as annotation blah 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 down here states. So yeah, it's a variable, it's within the scope, it gets freed at the end of the scope. We know this. Moving on. When a vector gets dropped, all of its contents are also dropped, meaning those integers it holds will be cleaned up. This may seem like a straightforward point, but it can get a bit more complicated when you start to introduce references to the elements of the vector. Let's tackle that next. I see what they're saying here. So they're saying, in this case where we have just integers, and when V goes out of scope, all these integers are going to go out of scope. However, given that a vector can hold any type, we can put a reference to a type in. Let's say, we're probably going to deal with strings next because strings are on the heap and you can have pointers to them. So we can have like a pointer to a type in here that's consistent throughout, and when V goes out of scope, do we really want those references to go out of scope? Reading elements of vectors. Now that you know how to create, update, and destroy vectors, knowing how to read their contents is a good next step. There are two ways to reference a value stored in a vector. In the examples, we've annotated the types of values that are returned from these functions for extra clarity. And listing 8-5 shows both methods of accessing a value in a vector, either with indexing syntax or the get method. Oh, that's cute. We can use a get or indexing. So right here we're printing out all of them, but if we wanted to print out, let's say, the third element, they did let third, and for clarity they put the type annotation there, equal a pointer to v, reference to the second element, well, third element in the array. Okay. And then print the third element is third. And then the second way they did was a get. And they put in a match, which I guess is kind of cool. Match v.get. Second one, index to third item. Sum, check to see if it's equal to third. That's sort of weird how they put that thing there well before I finish typing. And then if it is, print line, I'm gonna put this in a new, I'm gonna put this in a block so it looks better. Print third element is third, comma, none. Oh, I see what they did here. So the get gives you a result, enum, which is either some or none. Thus, it's safer to use. That makes sense. At least that's what I believe that's going on here. Put this one in a block as well. Print. There is no third element. I don't think I need a comma there. Let me run this, see what happens. Yep, it ran twice and I have a misspelled third. Okay, now if I said get element at index 10, which 10 does not exist, we only have 1, 2, 3, 4 in terms of indexing. See what happens? We say that there is no, it says third, but really 10th element index. That makes sense? That makes sense. Note 2 details here. First, we use the index value of 2 to get the third element. Vectors are indexed by number starting at 0. So what they're saying here is vectors here. This is the vector. When we start counting, we start from 0. So this is 0, 1, 2. 7 is the third element in the vector. Second, the two ways to get the third element are by using a pointer reference, the and, ampersand, and the brackets, which gives us a reference, or by using the get method. Second way you can get it is using the get method with the index passed as an argument, which gives us an option t. Earlier I said result, I really meant option. They give us an option, which is always going to be some or none. Rust has two ways to reference an element, so you can choose how the program behaves when you try to use an index value that the vector doesn't have. Wait, what? Rust has two ways to reference an element, so you can choose how the program behaves when you try to use an index value that the vector doesn't have an element for. As an example, let's see what a program will do if it has a vector that holds 5 elements and then tries to access the element at index 100, as shown below. These should not work. I'll write it anyway just to see what the error is explicitly, but at least for the get, if they wanted to, they can put it inside of a match and then use sum and none, and then that would compile. That just won't. Probably a runtime error. But let's see. Oh, I was writing it here. Let me call this one x equal vec macro. Pass it in 1, 2, 3, 4, 5, and let does not exist equal a pointer to v and index 100, and let does not exist equal v dot get 100. So the program panicked, so it was a runtime error, index out of bounds, length of 4. Oh, because I said v here instead of x. The x, change that. I meant x. Still would have been the same thing. But yes, index out of bounds, length of 5, but try to get index 100. However, if we just make that comment, I think this would work actually, because this returns an option and the options can't be none. So you can get something that's none. Yeah, that worked out. So it's just this one line that's erroring out. This line, since it returns an option, is fine. When we run this code, the first square brackets method will cause the program to panic because it references a non-existent element. This method is best used when you want your program to crash if there's an attempt to access an element past the end of the vector. When the get method is passed an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of the vector happens occasionally under normal circumstances. Your code will then have logic to handle having either some element or none, as discussed in chapter 6. For example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none value, you could tell the user how many items are in the current vector and give them another chance to enter a valid value. That would be more user-friendly than crashing the program due to a typo. Make sense? When the program has a valid reference, the borrow checker enforces the ownership and borrowing rules covered in chapter 4 to ensure this reference and any other references to the contents of the vector remain valid. Recall the rule that states you can't have mutable and immutable references in the same scope. That rule applies in listing 8-7, where we could hold a immutable reference to the first element in a vector and try to add an element to the end, which won't work. Okay, I'm starting to remember these rules. So here I believe they're going to demonstrate having a vector, creating a immutable reference to an element within the vector, and then trying to modify the vector. And that should yell at us. Type that out real quick. I'll use X. X could be my guinea pig. And I have to make X mutable. So let X is probably get rid of the beginnings because it's going to add extra output. And because it's gone, I can make UV now. Let first equal ampersand v index 0, and then try to do v dot push 6, because v is mutable, and then try to print the first element is first. Try to run that, see what happens. You yell at me. And you're yelling at me right here. Can I borrow v as mutable because it is also borrowed as immutable? Immutable borrow occurs here, right there, that's immutable. Mutable borrow occurs here when we try to add something to the vector. And that's another immutable borrow, but that's just this guy. Okay, so that's the error we got. The code in listing 8.7 might look like it should work. Why should a reference to the first element care about what changes at the end of the vector? This error is due to the way vectors work. Adding a new element onto the end of the vector might require allocating new memory and copying the old elements to the new space. If there isn't enough room to put all the elements next to each other where the vector currently is, in that case, the reference to the first element would be pointing to deallocated memory. The borrowing rules prevent programs from ending up in that situation. Okay, so what they're saying here basically is, let's say we have a vector, right? And we have a capacity of 5 and we have 5 elements in it. Somebody wants to, we create an immutable reference of the first one, like we have here with first, right? If we were to add a new element to this array, we're already at capacity 5. We can't fit the 6th one. So what happened is, underneath the hood, we have to change the space in memory that we're looking at, because this space in memory that we currently have isn't large enough. We ask the operating system, can you give us some more space? We find a new location with more space. This new one, let's say it has 10. We now have to copy over the first 5 to these first 5 slots, and then we can push the 6th one on. However, what just happened is we have mapped the memory of where these values are stored, like the in-memory mapping, to a new location. As such, this immutable reference first is no longer valid because that is still pointing to the old slide of memory that has already been deallocated. That is an issue, and because Rust does not want us to encounter that issue, they have rules in place to prevent that, which is this. What prevents it is we cannot change the size of the vector. We cannot add to it while we have immutable references in that same scope. Kind of cool. Continuing on. Note, for more on the implementation details of the vector type, see Rustonomicon. I don't know how to say this word. Rustonomicon and they have this URL. Real quick, let's just see what it points to. Oh, close that, close that, close that, close that, open this. And this looks like another book. Where are we? Oh, it points to chapter 9 of the same book. Wait, is it the same book? No. Ownership, chapter 3, type of persons. No, this is a different book. I don't know what book this is pointing to. Introduction. Oh, they're pointing to a section in another book. Okay. And this section is going to explain the implementations of vector. Understood. Yeah, they have another book that goes over implementation features, or documentation. Implementation details. There we go. Understood. Iterating over the values in a vector. If we want to access each element in a vector in turn, we can iterate through all of the elements rather than using indexes to access one at a time. Listing 8-8 shows how to use a for loop to get immutable references to each element in a vector of I32 values and print them out. They have a new vector there. I'm just going to use the one we have currently and write for I in pointer to V. We have our code block, and then we're just going to print out I. That's straightforward. I. Make this run. And we printed out 1, 2, 3, 4, 5, 6, which is the values that we have in there. We can also iterate over mutable references to each element in a mutable vector in order to make changes to all the elements. The for loop in listing 8-9 will add 50 to each element. Understood? Oh, so one thing to note is that in this example, I didn't change mine, but this vector is immutable. There is no mutable reference here, so you couldn't change it. Here, we have a mutable reference, so we can actually change the values of each of them. And that's what we're going to go about doing now. I don't have to change much. Oh, what's interesting is I didn't have to put mutable in front of it in order to iterate over it. Ah, I see. When I put mutable here, that means the instance that I'm looking at, the element that I'm looking at for the array at that index is going to be mutable. Understood. And then I can use the star syntax to add numbers to them. And then here I should probably just print everything out so we can see the new values. For I in pointer V, like we did before, print I. And this should work. And now we have 51, 52, 53, 54, 55, and 56. Understood? To change the value that the mutable reference refers to, we have to use the dereference operator, the star, to get the value in I before we can use the plus equals operator. We'll talk more about the dereference operator in the following the pointer to the value with the dereference operator section of chapter 15. Wow, that's an explicit title. Chapter 15. And I think they have a link to chapter 15, section 2. Understood? Using an enum to store multiple types. At the beginning of this chapter, we said that vectors can only store values that are the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need to store elements of a different type in a vector, we can define and use an enum. For example, say we want to get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating points, numbers, and some strings. We can define an enum whose variants will hold the different value types, and then all the enum variants will be considered the same type, that of the enum. Then we can create a vector that holds that enum, and so ultimately it holds different types. We've demonstrated this in listing 8-10, so right below. This makes sense. This makes sense to me. So what they're saying here is there are times when we want to have a vector that stores different types. And by definition, vectors cannot do that. However, enums have variants, and the variants can fit the need of being a specialized type while being under the same type, which is the enum type. In this case, we have spreadsheet. So let's do spreadsheet. So, and then we have our types. We have int, which is I32. We have float, which is F64. And we have text, which is a string. And then in our main, we can do things like let row equal vect, get the square brackets in there, and then start with our values. I'll just have in here spreadsheet cell, make this an int, give it a 3, spreadsheet cell, give it text, string, is strings? No, string, from blue. And then another one, spreadsheet cell, and make this one a float. 10.12. And semicolon at the end. Not exactly sure we can print this out. Well, I'm not sure how to print this out right now off the top of my head. However, we can see that we have no red squiggly lines. This looks fine. So what we ended up doing is we have our spreadsheet cell, which has 3 different variants: int, float, and text. But since they're all under the spreadsheet enum type, we can put them in our vector, and they'll stay then. Vectors will work just as vectors should work. And then for our different rows, we have, well, elements in our vector. Technically, I think this is just one row. We have an integer here, we have a string here, and we have a float here. Okay, moving onward. Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory on the heap will be needed to store each element. A second advantage is that we can be explicit about what types are allowed in this vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled, as discussed in chapter 6. Okay. When you're writing a program, if you don't know the exhaustive set of types the program will get at runtime to store in a vector, the enum technique won't work. Instead, you can use a trait object, which we'll cover in chapter 17. Understood. So let me go back here for a second. So what they were saying for this technique is that if while writing my program, I know all the different possible types or inputs that a function or a vector should or could have, then I can use an enum and put all my variants as those possible inputs. And then I can have a vector that holds that enum type with all the possible inputs. And then I can use match to iterate exhaustively over those inputs anytime anything is needed to be acted on. And if I did that, then I can ensure that I have covered each possibility that my program can run into. However, there are scenarios where you cannot predict and you do not know all the type of inputs your program will have. And in those scenarios, you cannot use an enum because the enum can only cover what you know ahead of time, not things you don't know. What they're saying here is that in those cases, you can use, you can use traits. The trait object right here, this is when they mention it. That will be covered in chapter 17. All right, continuing on. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined on vector by the standard library. For example, in addition to push, a pop method removes and returns the last element. Let's move on to the next collection type, strings. All right, I cut this video here and I'll move on to the next I'll do strings in the next video. Let me just make sure it says strings. Storing UTF-8 encoded text with strings. That'll be the next video. With that being said, I hope this was enjoyable. I hope it was useful. Thank you for watching. Peace.